Welcome to Careless Coder. Today we will continue with our maze from the previous lesson and implement scrolling up ourselves. Motherfucker! So in order to scroll up the screen, there are three methods that we can use. We can use indirect addressing, we can use unrolled loops, and we can use self-modifying code. We're going to explore indirect addressing and unrolled loops in this video. Self-modifying code, we will get there eventually, but this is already going to be quite long. Indirect addressing requires you to use the zero page. That's a new concept that we're going to explore, as well as we need to do 16-bit additions, because we keep adding 40 of course for each line to copy it. So we're going to introduce also 16-bit arithmetic. And then first we will have a look at the easy unrolled code that KickAssembler can generate for us. So let's jump in and have some fun. So yesterday we created this maze that we used the kernel call the character out to print this, but it's relatively slow. So today we're going to actually refactor our code to use two different methods. We're going to use unrolled code. That's basically hard coding a whole screen copy. So the 24 lines, we read the character on one line and we copy to the line above. And we do that for all the 25 lines. And we use KickAssembler to actually unroll this code for us. That is really the quickest way. And then the second example that we use is indirect addressing with 16-bit addition to actually do the multiplication. So let's jump in. So let's first copy this code, and I already did my test here. So that is the starting position. We're first going to remove all the stuff that we're not going to use. I'm actually going to also call this the generate random character in my get maze routine. We're not going to use this, but we're going to introduce a couple of new constants. Of course, the screen, because we're going to work with the screen memory, and the const screen bottom line, let's call it that. It's a bit shorter than screen bottom line. And that is memory position 07C. Basically 24 times 40. Right. And then we're going to create a new subroutine called, let's call this print maze line. So we're going to print a whole line of these slashes and backslashes on the bottom line. And each time that we completely wrote the bottom line, we will call a shift up to move the screen contents up. So let's first create this print maze line. We need an index register that we start to count from 0 for each of the characters on the line. So let me see what we're basically going to do. We're going to start on line 2. Let's put some data here. We're going to start on line 2. Let's put some more data there. Read this character. We subtract 40 from it and store it there. Read the next character, subtract 40 from it, store there. Read the next 40 from it from there. But we do that for each of these lines. So after we read this character, move it up. We're going to read this character, move it up. Now we're going to read that character and move it up. And that in essence will move up the whole screen. That is the algorithm. So we have the index character. We want to have a new char. Let's call that new char. We're going to get a new char. And since we moved the read from the random oscillator there, we don't need to do that in front of it. Then we're going to store that character that we read onto the, and I see it is in Z80 mode. I want my KickAssembler mode. Now it should actually bottom line, yes, there we go, bottom line, comma X, yeah. And then we need to increment X, compare X to 41, decimal 41, and there are 40 characters on the line, but since we already incremented here and tested, we need to add one. If it's not equal, then we branch to the new character, give me a new character, and otherwise we return from the subroutine. So let's, for now, check if we get a random line. This is basically our unit test. We test it by hand to see if we get a random line of content. Yes. Oh yeah, since we're not using the print character, we need to actually introduce some proper characters. And let's use 206 and 205. That is what the basic uses, and it's inverted. It looks nicer actually, I have to say. So that will work, yeah. And now we're going to implement this shift up, jump subroutine shift up, because we printed the whole line, and after that whole line we can shift it up and print the next line. Shift up. And we're going to use Unrolled code for this. So it generates a lot of code with the emphasis on it generates. And because you basically hard code the whole copy for the 24 lines, copying to the line above, it's wickedly fast. Faster than actually having to do it with indirect addressing and addition for the addresses that we're going to cover after we've done this. Because this we can do very quickly with KickAssembler. Again, we need a nice index counter in X, right? Because we need to count all the characters that we're going to copy. And basically what we're going to do is we're going to load from the screen plus the line number times 40, because that is the address of the second line. We start from the second line, we copy to the line above, and the third line, and we copy that to the second line, and the fourth line, we copy that to the third line. We're going to store that at basically the same position, minus 40. So it's on the same character position as the line above. And you could do a loop for this and actually do this calculation in math. That is what we do with the indirect addressing. We can do it easier with KickAssembler. We use a for statement. We already introduced the variable line, so let's use that. It's 1 because we start on line 2 and it's 0 base, so we start on line 1. Because if we copy line 0 upwards, we would actually copy it, I think, in basic RAM in this case. It's a bad idea. We don't want to do that. And if line is smaller than 25, then we do line plus plus, put the curly brackets around it, and that would actually do that. And now we need to actually still continue with incrementing the X position. So this block we have now 24 times for each of the lines, reading the line above and copying to its line above. That sounds confusing, but you guys are clever. You understand this stuff. And let's compare it to 40 or 28 hex. If it's equal, yeah, I need to invert this now. You usually see me branch not equal go to this label. But since this is more than 128 bytes of code, and the branch only allows you to branch up 128 this direction, 127 this direction, or vice versa, I always forget. We need to invert this logic. So if it's equal, we're going to jump to the RTS. because that is still less than 128 bytes. And here we can actually use the jump statement and jump over this massive block that's more than 128 bytes to this. And that should shift it up. Let's see if that is correct, my assumption. Yeah, so it printed this and it actually moved it up, so we can print the other line under there. So if we run it again, yeah, we see that we actually are moving up. So if we now just do the jump loop, remove the RTS, we have a very quick unrolled scroll routine. A really, really quick unrolled scroll routine. And if we compare that with this one that uses the char out, you can see the difference in speed. Now we're going to do the indirect way of shifting up. I'll let that run because I'm going to just change this. You know what? I copy it in this one. There we go. And we're going to re-implement. I copied the wrong code. I need to copy this one. So let's remove this. And let's add a different one instead of bottom line. Yeah, we still use the bottom line, of course. That's a constant called screen line 2. And that is actually a bit of a misnomer. It's always, of course, the line that you copy from. But since we start on 400, let's call it this. And we're going to introduce a new concept as well, which is called zero page. Let's pick up the zero page C64. If you want to use indirect addressing, you need the zero page to hold an address. Now you see most of them are reserved, but these, when you have BASIC enabled, which we still have, and the ROM, the kernel, we can use these for, and you can even override this if you don't use BASIC floating points. So we're going to actually store the 0400 begin address in FB and FC, and the 0428, that's the next line, in FD, FE. Then we can actually reference that with the Y counter and read from that address that we basically put in these two bytes of zero page. And that is indirect addressing. So let us first set up that zero page, because we're going to load the low byte from screen. And this arrow means the low byte, so screen is 0400. We're first going to store 00 in that FB, because this is a little engine, so we start with the smallest byte and then the highest byte. Where is it? Yeah, and we're going to store that, like I said, in FB. Then we're going to read the high byte from screen. And we're going to store that in FC, FB, FC. No, not frequency, FC. And let's do that for the next line that we're actually copying from, the source. So this is the destination block, the FB, and the FD is the source block. So we again going to read, but now the screen line 2. I should have called that source. Well, okay. And we need to store that in FD. Yes, FD. And then we're going to, we need to read the low byte. And let's copy this. And then we store the high byte in FE. And we actually have to count 24 lines now. So let's, or 24 lines, yes. So let's load X with 24. And we need to loop here to actually copy everything. And then we need to load Y. And Y is the register that you can only use for this indirect addressing. And we start with 0. And that basically is our character counter. And X is our row counter. And in the comments, in the code, I will be very explicit about this. So you can read that link below. So now we're going to actually read from the source into accumulator. And this is the indirect addressing. It's a curly, a round bracket. And then the beginning address. So that is where we're going to read from. And this is the offset. So currently this address contains 0428. So we're going to read the value, that's what this means, in 0428, where this pointer points to, with this offset. And then we can do the same with store. We can store it in the destination, that is FB, comma Y. And now we have basically copied it. Now we can increment Y to get the next one. We need to compare it with, compare Y with 40. Let's do the 28 hex, custom to it. And here we can use actually the branch backwards, branch not equal, because these are only a couple of bytes. Right, and then we need to actually, if we have copied all 28 characters of that source row to the destination, we need to multiply it by 40, or basically add 40 to it. And this is a new instruction. We need to clear the carry. CLC means clear carry, because we're going to actually add with carry. First, we need to load the value that is currently in FB, our low byte, and there we're going to add carry. I want to do 28, but let's do 4 hex, but let's do 40 for clarity's sake. So we're going to add 40, and we're going to store that back in FB. So now we have offset it. But if we roll over 255, then the carry is set. That's why the ADC is add with carry. So we need to also load, just to be sure, the high byte and add carry 0. If the carry is not set, then we do not add anything, because that's a 0 and the carry is 0, so then we do not set anything. And then we store that in FC. If we actually rolled over 255 here, then the carry is set, so we add 0 to it, but the carry is still there, so 1 is being added to FC, incrementing FC. And we also need to do the same, of course, again for our source. So we read from FBCD. We add 40, we store D, then we read E, and we store E, and then we need to decrement X again, because that is our line counter. So we now calculated the next line, decrement X, not dec. And we need to compare X. Actually, we can do it to 0, because it would actually... Yeah, we don't want to copy that first line like we said before. If we copy this up, we would actually copy it in something else than screen RAM. So jumping out earlier is correct. We can branch not equal to dash dash, right? Then we actually set it back to 0. Yeah, here we copy the individual characters on the line, and here the next line. Yeah, that's correct. And otherwise, we just return from string. So it seems like a lot more code, although the other one generates a lot more code. Let's build this, see if our... Oh, we have an error. There's always an error. 48. Where is 48? There. Oh. This doesn't need to be there. Did I copy it there? No. Okay. Let's see. Is it working in one go? It's working in one go. Now let's compare this with that one. It's a bit slower. Sorry, it's a bit faster than that one. That one is a bit slower. Now let's also build the unrolled one. That's this one, right? So, yeah. So that is the kernel call. This is the unrolled. And this is the indirect addressing. And you see that the unrolled code, although it generates a lot more code in bytes, is a lot faster because we do not have all these mathematics here. We do not need to have all these branches. We don't. So we have 25 lines that we need to copy here, and that is basically what we unrolled. So we just read through that code once instead of having to compare and doing the adds and the stores. So that's why you can actually see that. Which one is it? That one. This one is a bit faster even, despite generating more code. Let's see at how much code it actually generates. Can I see? So let's look at the published artifacts. So the lesson 4 was 56 bytes. That is using the print character. The 401 is 226 bytes. That's the unrolled code. And the indirect processing is 136 bytes. So despite this has more code, it is actually faster than the indirect addressing because we do not have to do all the additional math and do all the branching. So there you have it. 2 methods of scrolling the screen upwards really quickly. We can even see that the indirect is a bit slower than the unrolled loop as we expected. And we also had a look at the byte size. The differences in this case scenario aren't really too bad, to be honest. So go for performance, and it's easier as we saw. Now there is also self-modifying code. We will cover that in a different concept later on, but that basically would be a combination of these two, where we do the unrolled code. We actually would generate that offset the screen with the arithmetic that the macro now or the KickAssembler takes care of. It's something that we would generate ourselves, so based on that, and we would override that. That's why it's called self-modifying code. It's probably a tiny bit faster than the indirect, but still slower than the unrolled code. So I hope you learned something, and see you in the next one.